Okay, thank you for the nice introduction. I'm really happy to share our recent work at this workshop. So, my name is Siyuan Huang, and I work in Beijing Institute for General Artificial Intelligence, aka Big Data. And today I'm going to introduce some of our recent works and experience in how to teach the general agent to learn to interact and understand the 3D world. So here's a brief introduction about myself, and I graduated from UCLA and I started to work in a big lab for 3 years. And my long-term research goal is to tackle the problem of 3D understanding for the general purpose agent. And big AI is founded in 2020, and we have been looking for solutions, including research and engineering solutions for building the general agent. And we have published papers in vision, robotics, and body AI, and get few awards. So back to the talk today, and from the left side of the video, we can see that the current model, including the ChatGPT and Sora model, can already help humans to generate very realistic images, videos, and language. But however, we are still in need of a robot that can help us to do the household activities and to interact in the physical 3D world. And here is a video reviewed by 1X. This is their humanoid robot called Neo, and Neo can help humans to do some daily tasks such as bring the eggs and using knife to cut the pepper and etc. So actually, we are really need some robot who not only help us to creating content, but also helping us to do the physical work, like in household, in factory, and some public places. And to tackle this challenge, there's a paradigm shift for embodied AI in recent years. So previously, people tend to work on some limited tasks and with some closed world settings to train some specialist agents. But nowadays, people tend to address more sophisticated problems, such as involving the realistic 3D thing and open world settings. For example, the Open Vocabulary Mobile Motivation Challenge and today's VLA challenge. They all require the robot to navigate, to interact, and to grasp and pick and place the object in real 3D world. And they require the model to generate from one 3D thing to another. Another example is the Minecraft games that requires the player to create an agent that can finish some open world 3D task and to survive. And another paradigm shift is that previously people tend to focus on creating some specialist agent that can do certain, right? And you collect data for one task with hundreds of demonstrations, and you train that agent. But people are starting to focus more on the generate agent or foundational agent for the embodied AI. And there are some representative work like the Gato from DeepMind that's trying to solve the problem of vision, language, and robotics in one unified model. And of this work, I think they really are missing a very important dimension. And I think this dimension is the understanding of the complex 3D world. And as you can see, this is an example from a 3D semantic data set. And the color in the left video indicates different semantics in the 3D thing. And we can see that the semantics is really complicated from different colors, and the geometry is really intricate. So it is really hard for our current robot to understand such complex 3D things and to help humans do the 3D task. And let's see how current model behave in this 3D world. So here are some examples. For example, Google's RT series models, they can finish certain tasks in 1 or 2 3D things. And it's hard for them to generalize to other 3D things since the demonstrations are all selected in 1 or 2 3D things for long-term, like 70 months with certain robots. And it's still challenging for them to generalize to the new 3D things. And here's another example that people starting to use some video-based model to predict the next frame for the robotics model, and they're trying to help the robot to predict what kind of action should it perform. And on the right is an example from Sora. You can see that although Sora can generate relatively realistic videos, however, the physics in the video is still very impossible, and there are a lot of collisions and penetrations between the generated animals. And another example is the figure robot reviewed like 2 months ago. And we can see that the humanoid robot can perform taking place and doing some interactions with humans in a very predictable settings. But I think the problem is that the video is too clean, right? And there are only a few objects, and the task that can be performed is also limited, like in the video. So with all these challenges, I think there is a very important fact is that understanding how to understand the 3D world is a must for the future embodied AGI and robotics. And the underlying reason behind it is that understanding the 3D world is the primary challenge for connecting the perception and acting. And people from vision already know that currently the perception module are quite well. We can do the detection, segmentation. However, if you want to connect the perception to the acting, it's really hard since we don't have a very good understanding of the 3D world. I think like some new companies like spatial intelligence and the World Lab is trying also the work that Luca mentioned before is trying to tackle the problem of how to model the really complex 3D world. So the goal of our research is to build a general agent that can understand the 3D. So the general means that the agent can do a lot of things. For example, the basic stuff is that we can do the 3D perception, like the detection, segmentation, and reconstruction. And also we can do the 3D grounding. For example, if the input is a 3D thing, we can answer questions or refer to the certain object based on the command of the users. And we want our robot to do the 3D interactions, which means it can really interact with in the physical spaces, like opening the drawer or grab the cup on the table. So there are two ways of building such generous agent. And the first way is to build an end-to-end generous agent. That means we need to train a large model with multitask 3D data to train the end-to-end like foundation models. And this model can be end-to-end optimized, and it also can have a very unified and beautiful architectures. However, it needs to learn from multi-model and large-scale data, which is pretty hard for today's like 3D problems. And another very intuitive method is trying to build some modular, I call it hierarchical modular agent. And that means we can combine certain very powerful foundation model with the modular 3D models and skills. And we can leverage the powerfulness from the pre-trained VLM or pre-trained multimodal models and use them to serve as a brain for the like primitive skills and for the robot. And such model can possess like powerful reasoning and long horizon replanning capabilities and help the robot to do long horizon tasks. So today I will introduce two of our work that correspond to these two directions. And first is our recent work called Leo, an embodied generative agent that is published at SML this year. So the goal of Leo is trying to build an embodied generative agent that can help the agent to do a lot of stuff in the 3D domain. And the capability we expect the agent can have is including the perception, grounding, reasoning, planning, and acting. And there are a lot of tasks within this domain, such as the captioning, like question answering, the 3D dialogue, planning, and embodied navigation, and robot manipulation. And of course, if we want the robot to finish so many tasks, we need to collect a lot of data from different domains, from different dimensions. And there is a video showing that we collect data from the like object level, from scene level, and from the tabletop level, different levels of difficulties. And here's a video showing the capability of Leo. And so basically, we want the model and the agent to possess the capability of different dimensions, including the captioning and reasoning. So captioning means that given a 3D input, we want the model to describe what is existed in the 3D scenes, and they can answer certain questions based on the input. For example, where is certain object, where is the people located, and multi-answer on top of the drawer. And it requires very strong reasoning capabilities because even if we can detect each object, it's hard to understand the spatial relations among the objects. So the reasoning capability is trying to capture the like the relations among the objects and trying to use that relation to answer the question. Here's another example of inferring the relation between the object and answer the questions. And on another dimension, we want models to have some long horizon planning and dialogue capabilities. So the dialogue capabilities require the model to answer multi-round of interactions. For example, we can ask several questions about one object. And also we can ask the model to plan certain goals for the users. For example, here's a plan for a class, clean and organized nursery room. And we hope the agent can give us step-by-step plan for the robot or for the agent. And we also require that there's less hallucination in the response. And each step should be grounded on the 3D object and presented in the 3D thing. And at last, we want the model to have some acting capabilities. So first of all, the manipulation is the like most obvious acting capability we should have. And here we train the model by using some tabletop manipulation tasks, and we use the natural instructions as the input, and we require the model to perform certain pick and plays and more long-term like moving actions to finish the task. And at the last, we want the agent to have the capability to move. So we also train the model with the navigation tab, and the input for the model is an egocentric view and also the target image. And for example, this task is navigate to the toilet. So the model needs to observe the egocentric input and output the action space like turn around or turn right, turn left, or go straight, this kind of action. And finally, it should achieve the goal. So I will briefly describe like how the model is designed. So to design such a multi-model agent, a very intuitive way is to translate the solution into text, right? We do a lot of this stuff into the vision domain. However, it is very hard for the LLM or for some captain model to translate a very complex 3D thing into a sentence. So we have tried this method, but it doesn't work well. And previous method, like in the Minecraft, also reflect this phenomenon. So we have to give up the direct translation way. And another way to look at this problem is that we want some precise and very nice 3D representations for the 3D things. So we design a 3D encoder that can observe the object-centric representation and also the spatial relations between the objects. And the method we use that we utilize some object-centric point cloud features to extract the appearance and semantic information from each individual object. And then we use the spatial attention, which is a module designed for the 3D understanding. They're trying to capture the relative spatial relations between the objects, so it can have a sense of like the spatial relations between the objects. So in this way, we can not only extract the object-centric features, but also get the spatial relations among the objects. And after design the 3D encoder, we decide to use a very simple way to train our model, to train the agent. So the way we use that, we fine-tune the model based on an pre-trained LLM, which is the Vituna model in our context. And we use LoRa to model, to fine-tune the model. And we did not plan to like design very sophisticated laws. So we use a very intuitive, autoregressive, the most native way of like modeling such transformer-based agent. So we unify the different tasks into the unified task sequence. And for example, the task I mentioned before, we use the same format to formatting them into a unified task sequence, including the task prompt and including the action space. And also we integrate the token space of the text and action so that the LLM can predict them in a one for all task. And the objective is the native autoregressive loss, the trying to predict next token and next break. And to train the model, we use a two-stage training process. And the first stage is called Leo align. And the target of the first stage is trying to align the pre-trained LLM with the 3D things, right? The LLM, they know a lot of text information, but they have never seen any 3D object before. So in this stage, we use data to train the object captioning, object referring, and scene captioning. We want the model to have a sense of 3D. And in the second stage, we use we call the Leo the instruction tuning process that's trying to achieve certain high-level tasks based on the first stage, based on the result of the first stage. And here are some data sets we use, including object level data set, tabletop level data set, and some scene level data set. An important problem and very critical challenge in 3D is that we don't have enough data. So in our project, we use the GPT model for us to do the data generation. And we input the 3D scene graph based on the annotation of each 3D scene into the ChatGPT. And we ask the model about certain questions, and we want the ChatGPT model to generate us the correct answers. So in this way, we can elaborate the powerfulness of ChatGPT and save a lot of money by human annotations. So we all know that the LLM-based data generation, they have a problem of hallucination, sorry. And we also found the problem is very severe in our early explorations. For example, you will imagine or hallucinate the object that does not exist in 3D things, especially when the scene is pretty large. For example, might hallucinate there is a piano in the studio, which is not the truth. And the way we do is that we design an object-centric chain of thought method that we explicitly ask the model to predict the objects that it refers to. For example, the gray text means the intermediate result the model predicted. For example, it can need to predict which objects it refers and use that object to answer the questions. So in this way, we can solve the hallucination problem with a very high content, very high extent. And with the object-centered chain of thought, and also we design certain post-processing procedure for making sure that our generated data is of high quality. And we compared our models with similar papers called 3LM, and we especially compared on the problem that is highly influenced by the hallucination problem, such as counting existence and non-existence. And we find that after the object-centered chain of thought and also the refinement, we can get nearly 100% of the accuracy with our data generation pipeline. And we also compare perform tons of experiments of our Leo models, and including 3D VL benchmark, the referring, captioning, a lot of tasks, and also the manipulation and navigation tasks. And we find that the Leo performs greatly on these 3D VL tasks. And we, if you are interested, you can try our code online or publish it. So this is the first part of our model. So we want to explore how to train an end-to-end model for addressing and training the generative agent. And in the second part is we want to have a modular design, hierarchical modular design, modular agents for addressing the problem in which domain we don't have enough data to train the end-to-end model. And we tackle this problem called closed-loop open vocabulary mobile manipulation. So here's a video showing the process of how the system works. So the input for the robot is human instructions. For example, I'm hungry. Could you give me some food and pass me a cup of juice? This is totally open vocabulary, and we don't have any requirements of what we should say. And then the model needs to decompose the user input into different tasks and combine them with the primitive skills. For example, there are some perception capabilities of primitives skills, like reconstructing the 3D things and build a 3D scene graph and update the local graph and also grasp and interact. So these are all primitive skills. We're trying to combine the high-level planner with a lot of low-level different APIs or different primitive skills. And this system helps us to do this. And also we can use the GPT model as a planner to do the failure recovery. And here is another example of us using a Unity B2 robot to do the mobile manipulation. So here is the example that the robot needs to grasp the bottle on the table. However, during the execution, there's a human intervention that's trying to move the cup from the right side of the table to another. And the model needs to aware that it needs to adjust the plan and need to go to the another side to grab the bottle. So these capabilities require the model to have a very good understanding of the 3D environment and also has the capability to do failure recovery. And these two problems, I think, is rarely explored in current community. So there are two main challenges for the closed loop open vocabulary mobile manipulation. So closed loop means that we need to adjust our plan according to failures and we can recover from failures. So the first challenge is that we want the model to perform in the unseen 3D things. So it is very hard for the model to align the 3D semantics with the language. And the second challenge is that you need to do the closed loop replanning for failure recovery. For example, we saw a lot of VLM model nowadays and perform like 60 or 70% of accuracy or success rate. However, if the model fails, it's hard for them to recover from these failures and achieve a better or higher success rate. However, in our real daily life, we want the robot to have this capability of doing such failure recovery because the probability of recovery of failure is pretty high in the current robot system. And we propose two key modules to solve the challenges. And the first module is called Open Vocabulary Perception and Reasoning. So in this module, we use the computer vision method to build a 3D scene graph for the 3D scene. For example, we need the robot to go around the room first, and therefore it can have a low global map of the 3D scenes. And then we have a Go reasoner that's trying to using the image and also the user input to decompose the task into several primitive skills and or several steps. And also we have a more important module design, which is called the closed loop feedback and restorations. So it needs to do two things. The first thing is that module need to have the capability of verify what is the status of current task and whether the task is successfully executed. And the second capability is that it needs to restore from failures. It needs to propose what is the most probable or possible next stage actions that can save the robot from the failure. And here's a framework. So when the model fails, the GPT using the capture from the breaker can analyze why the model failed from the previous attempts. And after that, it can propose certain trials or certain next step plan for the model to do the plan restoring. And here is a more detailed decompositions. So first, the entire system is based on a code-based or code generation-based system. So that means for each step, the GPT or the models, the high-level planning model, need to generate certain code. They're trying to use the primitive skills to the next step plan. And the model can have a global and local perception module for capturing the global 3D semantics and also the dynamics happening in the table. For example, the case I introduced before, there are some dynamics or interventions in the table. So it needs to has the capability to update the 3D local 3D scene graph. And next, it should use the image or some more multimodal informations to do the status verification, so you can know what is the status of the task. For example, there are two types of verifications. The first is feasibility verifications. If there is a dirt cup, it is hard to use them to take clean water, so we need to wash the cup first. So here we can do the verification according to the task specification. And the second is the success verification. If we fail the task, we need the model to know why and how we failed the task, so we can plan the next move. And the last part is the model restorer. So it uses the experience of failure and use them to propose possible like next move. And we did some actually did some prompt engineering, right? Because we require the system to have a high level of autonomy. So we need to teach the VLM model how to behave in certain situations. So there are several parts. For example, in the task part, we ask the model to use the APIs of the primitive skills to finish the long-term task. And in the second part, we want the model to handle the feedback. So basically, we can print and read exceptions and analyze why the task is failed. And we have some tips for the step-by-step response. And also, we ask the robot to mind certain issues. For example, it can use the robot vision system to verify the grafting and placement result. And also, only navigate where necessary for energy saving. And if already positional suitable, navigation is not needed. And also, we ask the model to perform tasks in a step-by-step manner and verify each step before continue to the next step. So the whole process asks the model to have a very precise and explainable step of executing the plan and trying to recover from these clearly explained steps. And here we show some quantitative results of our models. So we did experiments on the mobile manipulations and also tabletop manipulations. We're trying to ask the robot to handle like various compositions of objects and 3D things. And also we did some experiments on the energy robot with the robot arm. And we asked the robot to like grab fish and wash fruits and deliver water. And also we designed certain interventions for the robot to test whether they can recover from the failures. And also we have some quantitative results. And the left side shows on tabletop and mobile tasks, the failure recovery actually improved the final success rate in a large margin. And on the right, we also analyze what kind of mistakes does the model usually encounter. For example, for the perception part, it has problems like the false positive misdetection and visual feedback error. And for the execution part, there are some problems like the API call error, but we met them a lot, and graph fail, which is also very common, and face fail and navigation fail. So we also analyze like what part of the model failed a lot and how can we improve them according to our method. So basically we propose two types of explorations for building a 3D generous agent that's trying to enhance the capability of understanding and interacting with the 3D things. And there are some pros and cons for each type of model. For example, for the end-to-end generous agents, it needs to solve the 3D perception within the models, which means it requires huge amount of data. And it's hard for them to do very long-term tasks because they can really start in this domain. And also the performance is scalable, which is the most largest advantage of the end-to-end model, right? And for the right side is the pros and cons for hierarchical modular agent. So first, it's easy to integrate with some strong and sophisticated 3D perception models. Right? We can do the reconstruction, we can do the grounding with some primitive modules. And also it requires small amount of data to do the training, which is beneficial if you don't have enough money and enough resource to have a huge amount of data. And third, you can do the long horizon reasoning and failure recovery thanks to the powerfulness of the foundation model. And last is that it will still suffer from error aggregations since it's a cascaded system. And also the system has a larger latency since there are some communication and connection problem with it among the modules. Yeah, here are the two works of our recent research, and I hope you like it. And they are or published. And if you have certain questions, you can contact me by email. Thank you.
Sure. All right, questions first.
Thank you for your call. And I think you are the leader of data acquisition library, and I'm also want to have to slide great reward your covers and also think there's there who work to the that.
Thank you for the question. So basically, I think the Tesla robot is really cool, and some people said that some of demo is teleoperated, right? But I think at least, although it might be teleoperated, at least it demonstrates the upper bound of the hardware system, like how smooth the action can be performed. And I think after certain levels of iterations, people can have train more and more fluid actions based on current hardware. So I'm very excited for their next step for the Bruno robot.
I have one question. So you showed you talked about very insightful pros and cons between two paradigm models. Could you talk more about like what's the bottleneck for each of the paradigm right now?
This is a very good question. So for the model of the left side end-to-end, the Jerry's model, I think the bottleneck still exists in the data region. So as long as we can collect enough data for certain downstream tasks, I don't think there will be a large problem for improving the components. And for the right side, the modular engine, I think the bottleneck is the last one, the error aggregation, and also the system agency that will make the experience not very pleasant during implementations.
Yes, sir. Hi, so thank you very much for the presentation. So my question is actually, so obviously 3D research or how to apply 3D into embodied AI is one of the kind of hotspots here. So my question is, so I just came from another workshop. So we were talking about 2D images plus depth information, right? So with depth and RGB, it's kind of like you can already do some embodied task manipulation or extraction. So my question is, so what's the advantage of using 3D compared to use RGB plus depth information in embodied AI? Does it make sense?
I think it's a great question. So I think the advantage of using RGB plus depth method is that we can leverage very powerful RGB-based or image-based models like the 2D models and other multimodal models. And they have a very comprehensive understanding of the long-tail distributions of the events and in the environments. I think this is an unique advantage. I think using the 3D representations, advantage is that we can have a more global captures or global understanding from the view. So we are saying that we want to understand the 3D world, 3D events from different perspectives. I think the 3D representations provide such perspectives for understanding an event from different views. Because we are doing some challenging tasks, the views are really dynamic, changing a lot, and also dynamics are really rich. So we need to have a more comprehensive and global understanding of the 3D world. And I think that's the main advantage of the 3D applications. And also, of course, we can combine the 2D like images with multi-view solutions to have a more efficient 3D applications. Yeah, I'm not sure this answers the question.
That's great.
Thank you.